Okay, everyone, we're going to start chapter 4, which is on the topic of integration. And the first section, 4.1, focuses on antiderivatives. So as you can imagine, an antiderivative is just the reverse of a derivative, right? So instead of asking, well, what is the derivative of x to the fifth, which you should know, I hope, just use the power rule, 5x to the fourth. We're asking the opposite question, right? The question we want to ask now is the derivative of what function is equal to 5x to the fourth. Okay, so we know what the derivative is. We want the original function that gave us that derivative. Okay. Now, I mean, the answer here should be obvious because we just did it, right? This is x to the fifth, right? So we say that x to the fifth is an antiderivative of 5x to the fourth. Okay. Now, right, notice I said an antiderivative, not the antiderivative. And because there's more than one. So, for example, if I take the derivative of x to the 5 plus 17, well, the derivative of x to the 5 is 5x to the 4, and the derivative of 17 is 0, right? The derivative of a constant is 0. So this is also just 5x to the fourth, right? So x to the 5 is an antiderivative of 5x to the fourth, but then so is x to the 5 plus 17, right? So x to the 5 plus 17 is also an antiderivative. I should abbreviate here, antiderivative of 5x to the fourth. Okay, and there's nothing magical about 17, right? I could have used any constant here. So the derivative of x to the 5 plus pi squared, right? Pi is a constant, so pi squared is a constant, is also 5x to the fourth, right? Plus 0, right? Be careful you don't do 2 pi here. The power rule doesn't apply to, right, because pi is a constant, right? So this is still 5x to the fourth, right? So it doesn't matter what this constant is, right? If I take the derivative of x to the 5 plus any constant, which I'll call c, I still get 5x to the fourth, right? So in this sense, we're going to call this x to the 5 plus c, x to the 5 plus any arbitrary constant, c can be any real number here, we can say this is the general antiderivative. Right. Of 5x to the 4. Right. Okay. So this is right. So this is going to be true for any antiderivative. You can always add an arbitrary constant because when you take the derivative of that constant will be 0. So it won't matter what that constant is. Okay, so let's try another example. In fact, here's, it's maybe only a slightly more difficult one than the one we just did. So suppose the question is to find an antiderivative, or in general, the general antiderivative of 2x, right? So What they're asking for is they want the derivative of what function is equal to 2x. So I hope you don't have to think too long about that, right? If you take the derivative of x squared by the power rule, you just get 2x, right? Plus any constant, right? So the derivative of x squared plus c is going to be 2x. So the answer, right, what's the general antiderivative of 2x? X squared plus c. And the way to check that, right, is to take the derivative of it. If you take the derivative of x squared plus c, yep, you get the 2x. Okay. Yep, try this one. Right, so again, find the antiderivative. So the derivative of what function is, let's just do cosine x. Right. So probably remember, or at least I hope you remember, that the derivative of sine is cosine, right? Again, plus sine plus any arbitrary constant. So the general antiderivative of cosine is sine of x plus c. Okay? So that's the idea of antiderivative. We're basically just going backwards here, right? So, if we have the functions over here, let me try to write function, right? And then over here we have their derivatives, right? So up until now, we've given you the function. So for example, 3x squared minus tangent x. And from there, you can take its derivative, right? The derivative would be 6x minus secant squared of x. Okay. But now we're going backwards, right? We're essentially going backwards. Suppose we know that the derivative of some function is, well, let's do 4x minus cosecant x. Okay, so if that's the derivative, what was the original function? Right? Well, let's think about this, right? If we had 2x, we did 2x earlier, that was just x squared, right? So how do you get 4x? Well, in some sense, you have to double it, right? You have to get 2x squared. So the derivative of 2x squared should be 4x, right? What about this minus cosecant squared? Well, I mean, if you remember, the derivative of tangent is secant squared. The derivative of cotangent, right, is negative cosecant squared. So, so it's not minus cotangent of x, because that would give you a plus cosecant squared. It's going to be plus cotangent, whose derivative is negative cosecant squared, right? Okay, so that's the idea, right? You've given the derivative and you want to work backwards to get your antiderivative. Right. And remember, these aren't the only answers, of course, because you can always add an arbitrary constant here, right? And you can add an arbitrary constant here to get the same derivative. So adding this c, this constant, does not affect what the derivative will end up being. Okay, so now let's introduce some notation for how we're going to express these antiderivatives. Okay, so for example, suppose we have that the derivative of y is equal to, let's do one we already know, 2x. Right? So essentially, if 2x is the derivative of y, what's y itself? How do we get y? Well, one way to think of this is that this is a ratio of dy to dx, right? We can think of this as a fraction, even though it's the symbol for the derivative. And we can multiply both sides by this dx. Right, so multiply by dx on the right, and then dx on the left. And then we can cancel the dx's as in any fraction. And now we have that the dy is equal to 2x times dx. Right. And you might be tempted to just divide by d, but remember, y and dy are two different things, right? This is not d times y. This dy is just the symbol for what's called an infinitesimal, right? And so we can't divide by d. What we can do, sort of the opposite of the d, which creates just a tiny part of y, a tiny fraction of y called the infinitesimal, we can add them all up by doing this long s. You can think of the long s as a kind of an infinite type of sum. But this symbol, this long s, is called an integral. Okay. So if you do that to the left side, you have to do the same thing to the right side, right? And so when you integrate, right, this is called integrating the dy. That's what gives you y, right? So this long s essentially cancels the d in some sense, being very informal about that, right? So in some sense, that's the answer, right? Y is the integral, the indefinite integral of 2x. And then the dx just tells you what's the variable of integration here, which is x, right? And of course, we knew the answer to this, right? This is just x squared plus some arbitrary constant. Okay? So from now on, when we want to find an antiderivative or what's called an indefinite integral, indefinite, and the reason why it's indefinite, of course, is because of the c, right? The idea is, right, we're going to use this symbol to do the process of what's called integration, right, which is the opposite of, or the inverse of what we've been doing, differentiation, taking the derivative. So if differentiation is taking the derivative, integration is taking an antiderivative, right? So here's another example, one that we recently did already. Suppose we want to find the indefinite integral of cosine of x. So again, the question is, what's an antiderivative of cosine? Well, the derivative of sine is cosine. So an antiderivative of cosine will be sine of x, right, plus c. Okay. So we can, let's try one more. Let's take an indefinite integral of sine of x. Right. So you might have to think about this for a second, right? So the question is, the derivative of what is equal to sine of x? Well, if you take cosine of x, the derivative of cosine is minus sine. So, but we don't want a minus sign, we want the integral of positive sine. So to get this to be a positive sign, you have to take the derivative of negative cosine, right? So that'll be a plus sine of x, right? Oh, no c here, right? It's the derivative of negative cosine is sine. It's, right, the derivative of negative cosine plus a c will give you sine of x. So in other words, the integral of sine x is negative cosine x, right, plus c. And one thing I should emphasize, of course, is that this x is sort of a dummy variable, right? If you want to do an integral of, let's say, sine of theta with respect to theta, right, then you just change the x to the angle theta, right? So this is just negative cosine of theta plus c, right? If you want to do the integral of 2t. With respect to t, well, we did 2x earlier. That's just x squared plus c. So this will be t squared plus c. Okay, so yes, you use whatever letter, whatever variable you're using, as long as it's the same here, right? So you have to be careful in the following sense. If you want to do an integral of 2x, but with respect to, let's say, t, well, that's a little tricky here because we don't exactly know what this x is in terms of t, right? X might be a function of t, right? Now, if it's not, let's say x is just a constant, right? With respect to t, x is just some number. In that case, the antiderivative would just be 2 times that number times t itself, right? So if you take the derivative of this, assuming that x is a constant, then the derivative of this will just be the constant, 2x. All right. So this is assuming that x is a constant, right? In other words, it does not depend on t. So independent of t. So the point is you're usually not going to see something like this very often. In most cases, it'll be either clear that this is a constant or it'll be clear what x is in terms of t, what that function is in terms of t. So hopefully you don't see this too often here because it can be a little confusing. Okay, so before we do any more examples, it might be helpful to figure out sort of the rules of integrals, just like we have rules for derivatives, okay? So, right. Right. So as the first rule, let's start with the simplest possible function I can think of is just 0. What's the integral of 0? Well, what would the corresponding rule for derivatives be? Right? If you take the derivative of any arbitrary constant, c, you get 0. So that tells me that the integral of 0 is just an arbitrary constant, c. Okay? What's the integral of, how about just 1? Well, if you take the derivative with respect to x of just x, right, you get 1. So the integral of 1 should just be x. Again, don't forget plus an arbitrary constant, right? So yeah, there was a plus c here. The derivative of x plus c is also 1, right? Okay. So what if I integrate any number, right? So it could be any constant. I don't want to use c, so I'll use a different letter, k. So here, k will be any constant, right? Well, if you take the derivative of k times x, right, plus any constant, sorry about that, plus any constant, right, you just get k back, right? So that tells me that this is just k times x plus c. Okay? And we can do even better than that. If you take the integral of k times any function, any arbitrary function, right? Well, we have the corresponding constant times function rule for derivatives, right? If you take the derivative of a constant times a function, it's just that constant times the derivative of that function, f prime of x, right? So the constant can come outside the derivative, so it only makes sense that the constant can also come outside the integral sign for the same reason. Okay? So, right, so we have the same rule for derivatives essentially applies to antiderivatives here. Now that might not be true for all rules, as we'll see later, but it is true for this particular one. And so I guess in that same In that same context here, suppose we want to integrate two functions, say f of x plus another function, g of x. Well, of course, we have the sum rule for derivatives, right? The derivative of f of x plus g of x is just the sum of the two derivatives, f prime of x plus g prime of x, right? So going backwards, of course, we expect that we can just integrate each function separately and then take their sum. So I have to write a little bit smaller here. I've got to squeeze this in. So we integrate f of x plus the integral of g of x. Right. So I'm not going to write plus c, of course, because we're not actually doing the integral here, right? This is just telling you what to do when you have the sum of two functions, right? Right. So it's just like the sum rule, except going backwards for integrals. Right. And if you remember, we actually used that in a previous example. I think I erased it, but yeah, it was in a previous example. So we'll end up doing more examples of this later. But right now, I just want to get to the rules here, right? So let's get to the important one, the one that we're going to use over and over again. It's the power rule. So what if I want to integrate x to any power n? In other words, what's the integral of x to the n? So let's think about this. We have the derivative. We know the derivative of x to the, I'll call it m here, is just m times x to the m minus 1. Right? So that's the power rule for derivatives, but we want to go the other way, right? So you can see that going backwards here, instead of subtracting 1, you're going to have to add 1, right? So in some sense, you're going to get x to the n plus 1, right? So if I take the derivative of x to the n plus 1, then I get n plus 1 times x to the n. Now, the problem is I didn't want this n plus 1 here, right? Because it's not here. It's not multiplying x to the n, right? So we're just going to have to do the opposite. We're going to have to divide by n plus 1. Okay? And then that gives you the result, right? So the derivative of x to the n plus 1 divided by n plus 1 is x to the n. And so the integral of x to the n is just going to be x to the n plus 1 divided by n plus 1, right? Plus an arbitrary constant c. Okay, right? And you can check. If you take the derivative of this, as we did here, you just get x to the n. Right? Now, there's one important exception to this before we go any further here, right? For the power rule for derivatives, this m here could be any real number at all, right? It could be any number, and this will actually give you the correct derivative. However, going backwards for antiderivatives, there's one very important exception here, right? So this is assuming that n is not negative 1. That's the only exception here. N can be any real number except for negative 1. So why not? What goes wrong? Well, let's see what happens. If we try to take the integral of x to the negative 1, and by the way, another way to write this would be the integral of just 1 over x. Well, let's use the power rule, right? This is going to be x to the power negative 1 plus 1 divided by negative 1 plus 1, right? So we get x to the 0, which is 1, but divided by 0, right? We get 1 over 0, right? So don't bother with the plus c here. 1 over 0 is not a number, right? This is undefined, right? And so, right, so the point is that this just doesn't work here, right? That this is not equal to this, right? So there is an antiderivative of x to the negative 1, but it's not 1 over 0, right? That's meaningless. It's an actual function. In fact, it is a function that you're probably familiar with. but it's not one we're gonna talk about until chapter 5. So some of you may even know what this is already, but if you don't worry about it, because for the time being it's not going to come up. Right. So at least in this whole chapter 4, you're not going to see the integral of x to the negative 1 or the integral of 1 over x. Okay, so that's the power rule for indefinite integrals or antiderivatives. Yep. So again, just like for derivatives, make sure you know this, right? Because we're going to use this over and over again. Right. So let's get to the other rules. Actually, there aren't that many. I think they're the trig functions now, right? So we've already seen the integral of sine of x is negative cosine of x plus c. The integral of cosine of x is sine of x plus c. So be careful where the minus sign goes, right? It's the integral of sine is negative cosine. The integral of cosine is positive sine. And we've already seen this one, right? If you integrate secant squared, right, you just get tangent, because the derivative of tangent is secant squared. And likewise, if you integrate cosecant squared of x, you just get negative cotangent of x, because the derivative of negative cotangent is cosecant squared, right? And then don't forget the plus c here. Okay. And then what about the others? So maybe we should think about this backwards now. Suppose we want to take the derivative of secant of x. So I hope you remember that one. It's just secant times tangent. Right? So for your antiderivative, if you take an antiderivative of secant times tangent, x, you just get secant of x. Okay. And, well, you probably remember the derivative of cosecant is negative cosecant cotangent. So the integral of cosecant times cotangent is negative cosecant plus c. Right. So those are the six formulas for the trig functions, for the integrals of trig functions. Now, you might not be very satisfied by this because that only raises more questions. It raises the question of, well, what is the integral of just tangent, right? I mean, we know the derivative of tangent is secant squared. What's the integral of tangent? Right, so that's a very good question, and it's one that we will answer eventually, but not until chapter 5. So again, this is not going to come up right now or anytime soon, right? And the same thing goes for the integral of cotangent. Obviously, we will get to that as well, but for now, we don't know what that is. And then there's the integral of secant, and then the integral of cosecant. So we will get to these in a few more weeks, but not quite yet. Okay, so for now, these are mysteries. Oh, you can look them up, of course, but it might not make much sense. You know, they're just formulas, and you know, when we get to chapter 5, we will actually derive these, or at least be able to figure them out somehow. But we don't have the particular function yet to be able to do that. Okay. One other thing about these things here is that we could rewrite them, of course, right? So, for example, right, secant times tangent, right? Well, if you remember, secant is just 1 over cosine of x, and tangent is just sine over cosine, sine x over cosine x, right? And so this is really just the integral of sine of x over cosine squared of x. Okay. And so what's the answer to this? Well, it's the same as the answer to this. It's just secant of x plus c, which I suppose you can also write as 1 over cosine of x, to keep the same format here, plus c. Right? But you'll notice something particular here, that you're not just integrating sine divided by cosine squared, right? In other words, you can't take the integral of the quotient is not the quotient of the integrals, right? And for that matter, for secant of x times tangent of x, you can't just integrate secant times tangent, right? That doesn't work. And so in general, this is a very big warning, because it's very tempting to do this here. So actually, I don't want to call it Rule 8. I just want to call it a warning, right? That if you want to integrate, say, a function f of x times g of x, well, what would you do? You would have to use a product rule, right? Now, there's a product rule for derivatives. And maybe I'll remind you of that. So I'm not going to use f and g here. I'll use u and v. So the derivative of u times v is just u times the derivative of v plus v times the derivative of u, right? So that's the product rule for derivatives. However, for antiderivatives, there just isn't any. There is no product rule. Right. So you might think that's nice, that's just one less thing to memorize, but that's a problem, right? If there's no product rule, that kind of makes integrals that you might think are easy, something like x times, sine of x, which, is a very easy derivative just by using the product rule, right? So you can take the derivative of x times sine x. So I'll let you figure that out. But to take the integral of x times sine x is a much more difficult problem. In fact, this is one we're not even going to tackle this semester. You have to wait until Calc 2, next semester, to be able to do something like this, right? Yeah, so there is no product rule. Likewise, there's no quotient rule either. Oh, I'm running out of space here. So there's no product rule and for integrals, and there's no quotient rule either. There's no quotient rule, right? And likewise, there's no chain rule either, right? So there's no chain rule, no product rule, and no quotient rule for integrals. Obviously, we have these for derivatives, but we want the corresponding formulas for integrals, and the sad fact is there just aren't any. And so that makes integration in general a much more difficult procedure than derivatives, because derivatives, you always have these formulas for the product or the quotient, but you don't have them for integrals. So to do something like this, we don't have a rule for it. We have what are called techniques, right? And once you get used to these techniques, things like this with the product is not that bad. But you have to get used to these techniques, and you'll do that, of course, in Calc 2, right? So, effectively, you can think of, instead of saying that there's no product rule, maybe it might be more accurate to say, to do the integral of a product, you have to learn some more techniques, right? So there's a procedure for doing things like this, but there's no procedure to do this in general. It highly depends on what these two functions are, right? And only some particular forms of this can be done using these techniques. Okay. So that's the kind of the drawback here. There's less to memorize, sure, but to do things like this, it becomes much more difficult. And that's why we put this off till next semester. Okay, so let's do a few more examples here. I lost count. I think we're up to example 8. That was rule 8. So I'll just call this example A. Right. Suppose we want to do the following indefinite integral. We want to do 12x cubed minus 15x squared plus 10. Okay. So this is a very reasonable question to do an integral like this. Right? This is just a sum or difference. Oh, I should have mentioned that the sum rule also works for differences, right? So just like for derivatives, the derivative of the difference is the difference of the derivatives. That's true for integrals as well, right? So we can split this up and just do the 3 separate integrals here, minus the integral of 15x squared dx. Don't forget the dx for each of these, right? Plus the integral of 10 dx. Right? So we have rules for all of these, right? And in fact, the 12 is a constant, so that can come outside the derivative. I'm sorry, the integral. These are integrals. Right? The 15 can come outside as well. And, well, so can the 10. If you take the 10 out, it would just be the integral of 1. But remember, we have the general formula here is that if you're integrating a constant with respect to x, you just get that constant times x, right? So we can do the last one right now and just say that this is 10 times x, right? And we're going to have c's here too, but I'll just have the c for all of them here. Okay? So yeah, the last integral hopefully was the easiest one, right? And now we still have to do these integrals, right? So we're not done. We have to perform these 2 integrals here. And what rule am I using here? Well, I have x to a power. So x to the n, just to remind you, it's x to the n plus 1 divided by n plus 1 plus c. Sorry, that's a plus 1, right? So, yep. So here n is 3. That's a 3. So 3 plus 1 would be 4, right? So this is going to be times x to the 4 divided by 4. Right, plus c, but we already have the c here. Right, so yeah, I mean, if you have, say, c1 plus c2 plus c3, that's just another c. So we already have the constant here, right? So minus 15, and now here, n is 2, so 2 plus 1 is 3, right? So this will be x to the 3 divided by 3, right? Divided by that new number. And then we already have the plus 10x plus c. We took care of that earlier. And so now we just divide 12 by 4 to get 3. So that's 3x to the 4th. Negative 15 divided by 3 is negative 5. So negative 5x to the 3 plus 10x plus c. And there we go, right? That should be the answer. There we go. And of course, I want to emphasize that you can always check. How do you check? Well, if this is our antiderivative, if I take the derivative of this, I should get this here. This, by the way, the thing that you're taking the integral of is sometimes called the integrand. It's the thing you're integrating, the integrand. So if I take the derivative of this, I should get the integrand, right? And so let's take the derivative. And we can do that quickly, right? We're used to this, right? So sum rule, power rule, constant times function rule. 3 times 4 is 12. And then, remember, for derivatives, you subtract 1. 4 minus 1 is 3, right? And then negative 5 times 3 is negative 15, times x to the 3 minus 1 is 2. And then the derivative of 10x is just 10. And the derivative of c is 0. So I'm not going to write plus 0. So, yep, that's definitely the integrand we hand up here. So, right, so we know this is correct. Okay. So So you can do this with any integral, right? Once you have your answer, you can always check by taking the derivative, right? Now, in some cases, taking the derivative might be just as hard as taking the integral, but not in this case, I think, right? And as with derivatives, when we first learned how to take derivatives, I didn't do this all at once, right? I did the sum rule, and then the constant times function rule, and the power rule. So I did it in stages, in steps, right, to get this. But we've done this so many times that I think you're hopefully all comfortable with taking the derivative like I did here, right, kind of doing it all at once. And eventually, you should get used to that as well. In other words, you should be able to do this whole thing pretty much all at once here. Okay, now it might take time for you to get accustomed to that, to get used to that. So for this example here, I did it step by step. I did it in stages using, each rule at a time. The sum rule first, and then the constant times function rule, and then the power rule. So that's what we did originally when we learned derivatives. But now that we're so used to derivatives that this is second nature, right? Doing this should be almost second nature by now. And so, yeah, when you're starting out to do integrals, feel free to take as many steps as you want here. But eventually you will get used to this, and this will almost be as second nature as it was for derivatives. So I hope that helps. Okay, let's do a few more examples here. So this is example B, I guess, since I'm using letters now. How about if we do the indefinite integral, or antiderivative, of, well, let's do x minus 3 times x squared plus 4. Well, you might think, wait a minute, this is f of x times g of x. This is a product. And earlier, I think I said that there's no product rule. And so you might think, we can't do this. We don't know how to do this. Think carefully here, right? Even though we want the integral here, you should remember how to take the derivative of x minus 3 times x squared plus 4. Right. And you say, well, yeah, I would use the product rule. Sure, you can use the product rule, right? But you don't have to, right? You don't have to. As long as you can multiply this out, right? Just use FOIL here. Before we take the derivative, let's just multiply it out first. We get x cubed, right? Minus 3x squared. I'm doing the inside first, right? And then plus 4x. And then negative 3 times 4 is negative 12. Right? So having expanded it out like this, now I don't need the product rule. I can just use the sum rule, right? And so the derivative will be very quickly 3x squared minus 6x plus 4, right, plus 0. Right? And so the same principle can be used here. Even though this is a product, this is one where you can multiply it out. In fact, we did that already, but now we're taking the integral of it instead of the derivative. We're taking the integral of x cubed minus 3x squared plus 4x minus 12, right, with respect to x, right? So at this point, having simplified this, or expanding it out, we do the same rule that we did in the previous problem. We just use the sum rule and difference rule, right? So maybe I should go step by step one more time here. So hang on, I'm going to erase the derivative, which was just a kind of a review of, using instead of using the product rule, multiplying it out first. Of course, if you use the product rule, you should eventually get the same answer as we did here. Okay, so I just cleared some space here, right? So now let's just do each integral separately. The integral of x to the 3 with respect to x, minus the integral of 3x squared, again with respect to x, plus the integral of 4x with respect to x, minus the integral of 12 with respect to x to dx, right? So I know it's kind of a nuisance to have to write this dx every time, but yeah, please do that. You have to declare what variable you're integrating with respect to here, right? So I don't ever want to see you write something like the integral of, 2x, because this is kind of meaningless at this point if you don't know what variable you're integrating with respect to, right? I mean, you can assume it's dx, but it doesn't have to be, right? It could be dy, in which case you get a different answer, right? So yeah, so the integral of 2x by itself is, for our purposes, is meaningless. So please write the dx after the function, right? Okay, so this is the power rule. N is 3. In fact, we did that one up here. So this is just 1 over 4 times x to the 4. But, or x to the 4 divided by 4. Same thing, right? And then, well, we should take the constant outside, right? The 3 is on the outside. And then when you integrate x squared, you get x cubed divided by 3, right? So in fact, the 3's cancel. And you just get x cubed, right? Plus 4 times the integral of x. The integral of x, well, this is x to the 1. Remember, yeah, I forgot to write down the exception here, right? N can't be negative 1, but it can be positive 1, of course, right? So 1 plus 1 is 2, so this is just x to the 2, x squared, divided by 2. And then minus the integral of 12 is just 12x, right? Don't forget the plus c. So we just have 1/4 x to the 4th minus x to the 3, because the 3's cancel. And then 4 divided by 2 is 2, so plus 2x squared minus 12x plus c. So, right. Oops, sorry. So that should be the answer to this. And again, the way we have to do it here, see, with derivatives, we could have done it either way. We could have used the product rule or expand it out first and then take the derivative, which is what we did earlier. Here, though, we don't have a choice. Because there is no product rule, we can't go from here to here directly. We have to expand it out first and then take the derivative using, take the antiderivative, rather, using the sum and difference rule here. Okay. Okay. Yes, let's do a few more. Example C. Let's do the integral of, how about this one? The square root of x plus 1 over, let's do the cube root of x. Okay, so this is a sum. There's no product here. So we can certainly use the sum rule. Oops. Okay. More space here. So, yeah, so that's just using the sum rule. And now you might think, well, I'm stuck because I don't know the integral of the square root of x, or the cube root of x for that matter. No, but what did you do when we took derivatives of the square root and the cube roots? Right? Remember, we used the power rule for derivatives. You can use the power rule here for antiderivatives, and maybe I should write that down again since we're going to use it. I mean, obviously, this is one you should just memorize at some point very soon. Plus c, right? And again, n cannot be negative 1, right? All right, so yes, when you use the power rule for derivatives, you change this to x to the power 1/2. So that's my n, right? That's my n, that's my exponent, plus, and then this is the integral of, well, x to the 1/3, but because it's in the denominator, right, it's x to the negative 1/3. Make sense? Yeah, so now we just apply the power rule. Here, n is 1/2, so 1/2 plus 1 is 1.5, or 3 over 2. Can I write it that way? Divided by the 3 over 2, right? Divided by 3 over 2. Right. Plus c, but we'll take care of that at the end, right? So let's do the second term here, x to the negative 1/3. So if n is negative 1/3 plus 1 is positive 2/3, right? And then divided by that n plus 1, divided by 2/3. Now don't forget your c here, right? So when you divide by a fraction, you're just multiplying by the reciprocal, right? This is actually 2/3 times x to the 3/2 plus 3/2 times x to the 2/3. So you kind of get the opposite, the reciprocal effect here, sort of. Right? And again, this is the answer. You can leave it like this. Or if you insist on writing it in terms of radicals again, you could write this as, let's say, 2 times x times the square root of x all over 3. Here, you can write this as 3 times the cube root of x squared over 2 plus c. So personally, I am not picky about this. Either way is fine. As long as you are fully comfortable in, translating from exponents to radicals or radicals to exponents, then either way is fine. That's a 3 there, right? Okay. And in fact, that's what we had to do in reverse, right? We had to translate these radicals into exponents to be able to use the power rule for integrals. Okay. So, yes. So the point is that this n here, this exponent, can be any real number, right? They can be fractions, decimals, right? And any real number as long as it's not -1. And yeah, we came close with negative 1/3, but negative 1/3 is not equal to -1. So we're safe in using the power rule here. Okay, so I think I want to do maybe 1 or 2 more examples. And there's plenty more in the homework. You should be doing a whole bunch of these in the homework. So I think we're up to example D already. And yes, so let's do the indefinite integral of 8x to the 5 minus 6x cubed plus 9, all divided by x squared with respect to x. Okay. Well, you can see this is a quotient, right? And if you wanted to take the derivative of this, you can use the quotient rule. But remember, there is no quotient rule for integrals, right? So I hope you're not fooled by this again, right? There's no quotient rule, so you might think you're stuck here, but it's the same problem we had with the product way up here, right? So remember what we did here? We had to expand this out and simplify it before we take the integral. And so that's the same idea here, right? Notice the denominator is just a single monomial term. And because of that, before we take the integral, right, so we still have to do the integral, but we can split this fraction up into the sum and difference of 3 fractions, right? We can write this as 8x to the 5 divided by x squared, dx with respect to x, right, minus the integral of 6x cubed divided by x squared. Oh, you know what? I'm using the sum rule already, which is fine. Like I say, you can get used to that. But let me write it as a single integral first. So 8x to the 5 over x squared minus 6x cubed over x squared, right, plus 9 over x squared. Okay, so I was maybe doing too many steps at once here. Okay, so everyone clear on the fact that we can split this single fraction into these 3 fractions here. After all, you have a common denominator. Going backwards, you're just adding and subtracting the terms in the numerator, right? Okay, right. Now we can apply the rules. In fact, I'm going to do 2 at once here. I'm going to bring out the 8. We can do that because it's a constant. And then this is x to the 5 divided by x squared, which I know you all know that that's x cubed. We'll do that next, right? Minus 6 times the integral of x cubed over x squared, which of course is just x. And then plus 9 times the integral of 1 over x squared, which is just x to the -2, right? So using the usual rules of algebra, rules of exponents, this is the integral of x cubed, right? So 8 times the integral of x cubed minus 6 times the integral of x plus 9 times the integral of, well, 1 over x squared. Yes, that's also a quotient, but we can get around that by writing this as x to the negative 2 and using the power rule. Right, using the power rule, right? Again, n is negative 2. It's not negative 1. So we're safe in using the power rule here as well. All right, so let's just use the power rule all 3 times here, right? So this is 8 times, if n is 3, n plus 1 is 4, so x to the 4 divided by 4, right? Minus 6 times, sorry, that's a 6. This is a 1, of course, so 1 plus 1 is 2. Which means you get x squared over 2 plus 9 times, so be careful, right? You're adding 1, you're not subtracting 1, right? So negative 2 plus 1 is negative 1, right? And then divide by negative 1, right? And since we took the integrals here, now this is the time to add the constant at the end. And then just simplifying, you get 2x to the 4, right? Minus 3x squared. And then 9 divided by negative 1 is just negative 9. And then x to the negative 1 is just 1 over x. So I would write it this way, although you could leave it as just negative 9x to the negative 1. Okay, so again, no quotient rule, but if you can simplify it first, split it up, then you're just using the sum and difference rule, right? Which works for integrals as well as it does for derivatives. Okay, I know this is a long video here. Oh, I'm running out of space again. So this is a long one because this is an entirely new concept. So I want to at least try to take you through it somewhat slowly here. So I think I want to do one more example, and then we'll move on to the next video, which is same section, just using this concept in an application. Okay, one final example, and I'm going to try to make this a tricky one, but I think it's one that might come up in the homework as well. So example E, we want to do the integral of cosine of x. You know what, we've been using x a lot here. Let's do theta. Cosine of theta divided by 1 minus the cosine squared of theta with respect to theta, of course, right? So d theta. Let me try that again. D theta. Okay. Okay. So again, we're confronted with the integral of a quotient, and so by now I hope you realize that you cannot just do the integral of cosine, right, divided by the integral of 1 minus cosine squared, right, and right, this doesn't work for derivatives, right? The derivative of this is not the derivative of cosine divided by the derivative of 1 minus cosine squared. So, of course, it doesn't work for integrals either, right? So get that out of your head because it never works, right? It just doesn't work. Right, so what did we do when we had the previous problem had a quotient as well? It was a fraction. Well, we simplified it, right? We split it up and we wrote it as 3 separate fractions. Now, you can't do that here because the difference is in the denominator. So yeah, for just like this doesn't work, you can't do cosine divided by 1 minus cosine divided by cosine squared, right? That doesn't work. Okay. So we need to be a little bit more clever about this, right? That's why this is a tricky one. If you look at the denominator carefully, this should look somewhat familiar. If you remember from your trigonometry days, your pre-calc days, if I take the sine squared of theta plus the cosine squared of theta, that's our Pythagorean identity. This is always equal to 1 for any angle theta. So if I subtract the cosine squared from both sides, right, I now have that sine squared theta is the same as 1 minus the cosine squared of theta. So there's our denominator, right? It's the same as sine squared theta. So I can replace the denominator, 1 minus cosine squared, with just sine squared. Okay, tricky, right? And I think this is one we saw before, or maybe in a slightly different form. Because you might be wondering, this is still a quotient, and if there's no quotient rule, then I'm still stuck, right? I can't do anything. True, right? There's no quotient rule, right? So we can't split this up either, right? We cannot do the integral of cosine divided by the integral of sine squared. For one thing, we don't even know the integral of sine squared, right? That's actually a slightly harder problem. So why don't we think of this as just cosine over sine? Cosine over sine. Let me do 1 over sine first, times the cosine over the sine. Right. So effectively, I did split this up, but as a product, right? After all, sine times sine is sine squared. Right. So again, it feels like a trick, but remember, sine 1 over sine, you should remember as cosecant of theta, and cosine over sine is cotangent of theta. And if you go way back, this was one of our rules. The integral of cosecant times cotangent, well, the derivative of, getting confused here. The derivative of cosecant of theta is negative cosecant cotangent. So that means we need a minus sign here, right, plus c. So I think that does it, right? There's our answer. But this was a tricky one, right? So the integral of cosine theta over 1 minus cosine squared theta, after all that, is just negative cosecant theta. Or, if you prefer, negative 1 over sine theta, right? Oh, plus c. Oops, plus c. But that's not obvious. Certainly, just looking at this, you would never suspect that it's something this simple here. So, yeah, so this was a tricky one. You really had to use the Pythagorean identity. So, yeah, right, this is one you really probably should know. Oops. All right, this here. All right, I did the subtracting the cosine squared, but sine squared plus cosine squared equals 1. That came in very handy here to be able to write 1 minus cosine squared as sine squared, and then to be able to do this, right? So this one, you kind of had to be very clever to do something like this here, but that's how it's done. Right. So I think we'll leave it at that for the examples of just the integrals here.